Hi, I am Mustansar Fiaz. Today I am going to present DDAM-PS, Intelligent Domain Adaptive Mixer for Person Search, and my teammates are Mohammed, Khaleed and Hisham Cholakkal. So, what is a person search? Person search is a fundamental computer game problem where objective is to locate, identify the query person in a gallery of all seen images. For example, the query person in the left side, we need to find the query person in the gallery on the right side images. While the person search has been extensively explored under fully supervised learning and weakly supervised learning paradigms, adapting it for unsupervised domain adaptation generalization remains challenging as there is a significant disparity between the distribution of the target and source domains. Unlike fully supervised and weakly supervised, UDA focuses on bridging the gap between the ideal training set and real world scenarios by leveraging the labels, source data, and transferring the learned knowledge to the unlabeled target domains. DApps is the first UDA method that employs implicit alignment modules that implicit alignment modules and pseudo labeling to reduce the disparity between the source and target domains. However, DApp suffers from a lack of an explicit bridge to determine which crucial information, such as similarity or dissimilarity, should be utilized to mitigate the domain disparity. However, the implicit alignment modules employed in challenging and reliable scenarios where the person search model encounters scene challenging like Boolean pose variations as well as environmental changes such as adverse indoor and outdoor distributions may deteriorate the region of interest. In addition, the normative embeddings to disentangle the two subtasks that is detection and re-identification. However, it is still utilize shared weights for both detection and REID, therefore directly utilizing shared any representation for the domain adaptation may further increase the complexity of the person search. This is overall framework of our proposed intelligent domain adaptive mixer for person search. So it jointly takes input from both the source and target domains. The base network of our framework is DApps, which incorporates an implicit domain alignment module, DAM, to reduce the gap between the two domains. So the source and target domain images are fed to a SNet50 backbone network to extract features embeddings. These feature embeddings are then input to RPin to generate ROA aligned proposal candidates. To enhance the re-edit task within the baseline, we introduce a intelligent domain adaptive mixing DDM mechanism. This mechanism aims to smooth out the extreme differences between the source and target domains, allowing for better domain adaptation. To achieve this, we fuse the source and target domains proposals to generate new mixed domain proposal representations. For detection tasks, we employ a combination of box regression and person versus background classification to compute detection losses. For re-ID tasks, we impose OIM re-ID loss on the source and target domain features. Pseudo labels for the target domains are generated using clustering strategy. In DDM, the source and target ROI pool features are realized with the average and max pooling operations. These pool features are then concatenated for each domain and passed through a shared fully connected layers. These features from the fully connected layers are merged via element submission operation and input to a multi-layer perceptron MLP followed by a softmax function yielding the domain constraint weights. Finally, the ROI mixed domain representation are achieved by mixing the source ROI features and the target ROI features using the two domain constraints. In order to generate the moderate mixed domain adaptive representations, we introduce two bridge losses and a disparity loss. The the F bridge loss is implied by utilizing the NA embedding of the target domain, source domain, and mixed representation to evaluate the distance across the domains. On the other hand, the alpha bridge loss is enforced using a hybrid memory projection modules to measure the disparity between the mixed domain memory projections and the two domains. So Additionally, we employ disparity laws to regulate the domain mixing mechanism using constraints CS and CT obtained from the DDM module to prevent from overfitting to either of the two extreme domains. As mentioned earlier, the person search models face challenges in jointly optimizing the two subtasks, that is object to direction and REID. When adopting these modules for UDA, the complexity may further increase. So to address this, we propose a decoupled norm where embeddings any this decoupling may not only alleviates the conflict between the two subtasks but also improves the person search domain adoption performance. Inspired by the intermediate domain adoption mixing idiom, we aim to enhance the knowledge transfer between the source and target domains by learning mixed domain representation for both domains. The effectiveness of domain mixing can be handled by two factors, that is, the ROI pool feature sample. Feature samples often exhibit diverse background, and individuals within the both intra-domain and inter-domain distribution may experience appearance variations. This includes challenges related to environmental factors such as indoor and outdoor scenes. Another is using DDM, we can generate infinite number of mixed representations by exploring source and target domains ROI features for the DDM using the DDM modules. However, only a limited portion of these mixed domain representation is capable of effectively bridging the gap between the two extreme domains. These factors can potentially degrade the quality of the mixed domain representation. To bridge the two extremes in the hyperspace, the distance should be proportional such that CS plus CT is equal to 1, and uh, the moderate mixed domain representation can be obtained using or domain constraint weights by identifying the closest path to the both source and distribution and target distribution, as well as localized along the shortest path. The problem can be minimized using this loss function. This loss function controls the gap between the two domains by minimizing the shift between the two domains, and the domain constraint weights in DDM ensures a steady domain adaptive procedure to balance the minimization of domain shift from source to target domains. We impose bridge losses on mixed domain representation and fit to NA for re-ID tasks. Therefore, we extend our OIM loss for the UDA loss and introduce a hybrid projection memory projection to keep the lookup table for known source IDs and pseudo target IDs. However, single CQ for the both and target known identities uh, and using hybrid memory for extended OM, we can calculate the similarity projection for the input features with respect to the lookup tables IDs. Finally, the losses for the alpha and bridge losses can be computed using this loss function. So to maximize the diversity of the domain constraint weights, we should utilize disparity loss using this function. This integrates that mixed domain representation are as much diverse as possible to maintain the shortest destination path property. Qualitative comparison on fully supervised, weakly supervised, and UDA methods shows that our method achieves favorable performance. Qualitative results shows that our methods can detect better person compared to baseline depths. Our ablation studies shows that integrating our contribution, that is disparity loss as well as to bridge loss, results in better performance. Moreover, the decoupling the NA further improves the performance. Thank you.